Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
We're going to be using calculus to talk a lot about maximum and minimum values and how they appear in graphs and what we can do to calculate them without technology. Now, sometimes graphs will have an absolute max or min, and that would be like the highest or lowest it ever goes. So, highest or lowest y value. And that would be in the entire domain. What we often talk about, though, is the local max and min. Now, you can only have one absolute max or one absolute maximum, absolute minimum. You might have more than one. But with local max and min, it can occur multiple times. So that's just going to be looking on an interval. So same idea, but this is going to be on an interval, where this is on the entire domain. Okay? So let's check out just a rough sketch here. Okay, here's a quartic function. We happen to have three locations where you could consider them local maxes or mins, but we only have one absolute minimum. These are both locals, and this could be considered a local as well, because you could talk about it on a domain. Okay? So if you'll notice, the local max and min happen to exist when you switch between going downhill to uphill or uphill to downhill. Okay? So let's think about what that means. And I'm going to draw a nice soft curve so we can really talk about this. I'll call this A, this B, and this C. So I think we would all agree here that the slope of this is going down, which means our derivative is less than 0. Here our slope is going up, which means our derivative is greater than 0. We're going down again, so less than 0. And here we'd be going up. Now note, the derivative is equal to 0 at A, B, and C. And that's where the switch happens, right? When the derivative is at 0, we're usually switching from positive to negative. The reason why I say usually is there are occasions for where we don't make a switch. But if you're going downhill and then uphill, you know that switch has happened. Okay? So just an example of when it. Here we can see that we hit a 0 slope tangent line, but this graph is always going uphill. So even though we hit a 0 slope, it did not mean that the slope that we went from uphill to downhill. It just meant we kind of paused and then took back off again. Okay, it'd be like stopping at a stoplight and then continuing forward. So you pull up to the stoplight, you pause, and then you take off from the stoplight. So we really need that switch in direction from negative to positive to have a maximum or a minimum. So Fermat's theorem. Unfortunately, we don't normally do a lot of proofs in calculus, so you don't have to remember all the words. But it's important to use them when we can. Okay? If a local maximum or minimum occurs, at C, and the derivative at C exists, then the derivative at c is 0. Which, I mean, that makes sense because you have to hit a 0 slope to switch between positive and negative. However, it is really important to note that the derivative at c has to exist. Because, remember, derivatives have to happen on smooth continuous. So if it's a cusp like this, then the derivative at c does not exist, and Fermat's theorem isn't a guarantee. Okay? Now, if they give you a certain window, this is kind of important. If they say, find all extrema on an interval A to B, your max or your min can occur at the endpoint. I forgot my second C. So that's something we have to make sure we check if we're trying to find all extrema, like what is the maximum, what is the minimum. If they're limiting us to an interval, there's a highest point on the interval and there's a lowest point on the interval. It's our job to make sure that we check, okay? So things that you should always check, i.e. critical numbers, okay? Critical numbers happen where your max or min or potentially are. Okay. They are numbers where the derivative equals 0, the derivative is undefined, and f of a and f of b. Okay. F of a and f of b, assuming they've given you an interval. All right, so let's try this out. F of x equals x to the third minus 3x squared. Okay, we know cubic functions usually do this. We're not always guaranteed that extra curvature in there, but that's normally what happens. So we would assume there would be one maximum and one minimum just from what we know about cubic functions. So let's go ahead and derive this. We've got our derivative here. Critical numbers happen when our derivative equals 0. So we'll factor this one. So it looks like 0 or 2. So, well, I'm going to test negative 10 into here. Or you know what we know about it. This is a quadratic or a parabola, correct? So the parabola would be above the x-axis, then below, then above, right? Above is greater than 0, below is less than 0, and above is greater than 0. See how we're going uphill, downhill, uphill? So this must happen at the ordered pair 0, comma something, and this must happen at the ordered pair 2, comma something. Let's pop those in. That would be 0, 0. 8 minus 12, that would be negative 4. So a local maximum is at 0, 0, and a local minimum is at 2, negative 4. Not global. Local max of 0, local min of negative 4, and the full ordered pairs of the location. Now, could you check that with graphing? Absolutely. And we can clearly see that, yes, we were correct. So see how that makes that minimum? So instead of using graphing technology, we can now use our derivatives to find out where those switches happen, which is a really powerful tool. Okay? So let's check out f of x equals x cubed. the derivative would be 3x squared. And if I set that equal to 0, x would be 0. Now here's the thing, it's a parabola, right? Quadratic is a parabola. Parabolas make... So here it's greater than 0. And here it's above 0. So why were we not getting that switch? Ah, that's that we pulled up to a stoplight and then took off kind of thing, right? So there is no local max or min in this case, because we didn't ever switch directions. This kept going up. It was a critical number, yes, but it did not have a change of direction, therefore there was no maximum or minimum. All right. What about one of these kind of functions? Okay, so this is not differentiable because it's smooth and continuous. So in order to make it differential, we need to rewrite it. Hopefully you know -3 is the critical number because that's what zeroes it out. And absolute values make V's. You've probably already seen where this is going. So the left side would be negative x plus 3, and the right side would be positive x plus 3. And the switch would happen at -3. So when x is less than -3, when x is greater than -3. Which one are we at when we're at -3? That's up to you to choose. I don't care. One of them needs to be underlined. However, this is not differentiable. F prime of -3 is undefined. Why is that? Well, when we derive the top, the derivative of x is going to have two different derivatives. One for when x is less than -3, and that's going to be a slope of -1, or a derivative of -1. This will be a derivative of +1. At -3, it's undefined. We don't know whether we're going downhill or uphill. So we can't actually include it here. So -3 becomes a critical number. When we check that critical number, we do find that we switch from downhill to uphill, making -3, 0, the minimum ordered pair. And this one happens to also be a global minimum. And that's because the graph was not smooth and continuous at the absolute value point. So in order to derive absolute values, you must make them a piecewise function. However, most people can get the slope of an absolute value pretty quickly. All right, so find all extrema on f of x equals 3x to the 4th minus 4x cubed on the interval -1 to 2. Okay, so we know quartic functions can look like this, right? But they only want us to pick part of the window. And I'm guesstimating here. They're not wanting us to pick the whole window. So, critical numbers. We've got -1 and +2 as critical numbers, and that's because that's our A value and our B value. But we also have to derive to get our remaining critical numbers. So we've got 12x cubed minus 12x squared. We'll go ahead and factor that. 12x squared would leave me with x minus 1. That's cubic, and that's a bounce. I didn't write that very clearly. 12x squared, x minus 1. Because it's squared at 0, we know that's a bounce. 1 would be a cut. So we're going to get this kind of thing going on. So below 0, below 0. So f prime of x is less than 0, then greater than 0. So 1 is going to be an important number. 0 is going to be a critical number as well. but we're not going to see a change in direction here. So, but we will go ahead and check it as well. All right, so if I were to substitute 0, I'd get 0. If I would substitute 1, I'd get -1. 2, let's see, 1648. That'll come 16. That'll be 3 plus 4 is 7. Okay, so out of all these points, we can tell this is definitely the maximum. And we can tell that this is definitely the minimum. Okay, but they told us to make sure we just graphed it. 3x to the 4th minus 4x to the 3rd. And they only wanted us to check between -1 and 2. They didn't want to see the whole graph. Okay, so here we can see why we saw something at 0. They were backing up, they paused, and then they continued backing up. Then they started going forward again. Okay? So we definitely can tell that although -1 was higher than this point here, this was most definitely not the highest point in the graph. Over here was. But we can see 7 and 16 were both high. 0, 0 was a point of interest, but it turned out to not be a relative max or min, and 1, -1 was definitely our global minimum. So notice we checked both endpoints as well as any critical numbers that we got from the derivative.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.